Today we're talking about something different though. It's not really the physics principle that's important. It's a mathematical thing you need to be able to do. It is very likely on your exam that you will hear the phrase, how's it put? It's usually put very specifically. Create but do not solve a differential equation. That could be used to, and then there'll be something after that. Then part B, solve the differential equation. So that is incredibly common. And what's really important to understand is that they've broken it up. In the old exam, they would not have that part about create but do not solve. So they have clearly tried to separate it out. What's important to note is that it's worth more points to create and do not solve the differential equation than it is to solve it. However, it takes a lot more time to solve the differential equation than it does to create it. Now, a lot of you are going to think that this is calculus. It's not. It's differential equations. Differential equations uses calculus sometimes, and also uses a lot of other methods to solve differential equations. You are going to be taught a single method that is the most common. There's only 2, maybe 3 problems that they can possibly ask on the AP exam that have to do with differential equations. So they are all the same. Once you learn how to do this, all you really need to do is repeat it every week so that you are not scared of it and you know what to do. And any variation that crops up will cover every single one of them. So you will see this problem a lot every week. And I will force you to write all the steps out and submit it so I can see that you're writing them all out. And then at least once, I'm going to make you do it all right here in class to show me that you can do it. Does everybody understand? It's just too prescriptive not for you to do this, even though the actual math is pretty challenging. So today, I'm not going to use any calculus. I'm going to show you that they've already done the calculus for you. You just have to recognize it. But then later on, I'll show you how to do the calculus. So we are going to be talking today, the example we're going to be talking about is air resistance or air drag. And it's going to be based on a lab we're going to do sometime. I have to work it in. It doesn't fit in with anything that we are doing right now and won't for the rest of the year. So just sometime when we're between topics or we need a break, we're going to do the coffee filter lab, which is just dropping coffee filters. It's a pretty straightforward lab. When you drop a coffee filter through the air, the coffee filter will experience a downward force due to gravity. That's a big duh, and everybody knows that. However, the reason why we use a coffee filter is that the coffee filter is very light and has a large cross-sectional area compared to its weight. Because of that, air resistance can't be ignored. When the coffee filter is traveling slow, it will part the air as if it's passing through layers of air. We call this kind of air resistance laminar drag because the object is not significantly disturbing the layers of air. Now, if it's going fast enough, you will reach turbulent drag. Turbulent drag is when the layers themselves don't part naturally and you begin to get vortexes or air that's curled or air that's creating pockets of vacuum or pockets of high pressure. That's what happens when a plane reaches some kind of disturbed air. They call it turbulence, but a plane can create its own turbulence by disturbing the air. The lab itself, though, never has the coffee filter go so fast that it creates turbulence. That's going to always be in a form of drag called laminar drag. Now, the reason why that's important for me to explain is because laminar drag is a type of drag that is proportional to the velocity, meaning the drag force is equal to some constant times the velocity. Now, in 6th period, I made the constant a lowercase k. In this period, I made the constant a lowercase c. It doesn't matter what I use here. They switch it up all the time on the AP exam. Don't become accustomed to it. It just means that it's proportional to the velocity. The truth is, this is actually a collection of things that describe the coffee filter. Its shape, its cross-sectional area, its mass to area ratio, all of these things actually make a difference in what the value for C is. So things that are more aerodynamic will have a smaller value for C because you get less drag for your velocity. But something like a parachute, a parachute is specifically designed to have a very high value for C so that you get lots of drag. The coffee filter is pretty high. It's not particularly well shaped. So my Jeep, high value for C. A Prius, low value for C. I drive basically a Borg cube down the street. But something that's nice and aerodynamic, it cuts through the air cleanly. You guys have seen all the things they put on the trucks on the highway to make them appear to cut through the air a little bit cleanly. Little flaps they put on the back of the truck to try and allow the air to bend around the back of the truck more cleanly. If you haven't, just look at any of those big 18-wheelers. The stuff that's between the wheels that looks like pieces of metal, that's actually designed to create aerodynamic, less vortexes and more laminar flow of air around the trucks. They have lots of stuff trying to do that. Now, the drag force is against the direction of motion. So truthfully, I should put a minus sign here. But if I put the minus sign here, and in a few minutes, you'll see why I don't like to. Because the minus sign tells us the direction. And so I try to be careful about when I throw a minus sign in there. Drag is always against the direction of motion. But what that means is in my picture here, I'm just going to draw that as an upwards arrow and write CV. So nobody should ask me why I didn't make the CV negative now. I used a negative to indicate the direction of this force. Now, you guys might not be sophisticated enough to understand why I'm choosing this example, but I hope that you are. This is an interesting circumstance. I want you to consider what happens. When you first release the coffee filter, how fast is it going? What's that? 0. When I first release the coffee filter, at time 0, the drag force equals 0 because it's not moving. This is at t equals 0. Well, this clearly suggests that the coffee filter is experiencing an unbalanced force and will accelerate downwards due to the action of gravity. So, sometime later, just an instant or two later, the object, because it has accelerated, will still have the same weight downwards, but now will have a small force upwards representing the force of drag. Not much, but some. It's still accelerating downwards though, which means it's still getting faster. And because it's getting faster, the drag force is also getting faster. But it's still accelerating downwards. So it's still getting faster. And so the drag force will be getting faster. Now I can draw many of these little pictures, but what I'm going to do is skip to the end when it reaches what's called the steady state condition. Problems like this that have a dynamic force may sometimes reach a steady state condition, a condition in which the net force finally makes it to 0. There is a time when the velocity will grow great enough so that the drag force will be equal to the weight. At that moment, there'll be no change in the velocity. It will no longer accelerate. So at that moment, we're at a special condition called terminal velocity. And you can find out what the terminal velocity is without doing hardly any math. Right now, the terminal velocity occurs when the net force equals 0. If I haven't made that abundantly clear, you should put that in your notes. I think it's obvious, but a lot of students don't, and they get the first question wrong on one of these, which is, what is the terminal velocity? Well, it's when net force equals 0. It's when Vt equals mg over c. Net force equals 0. So those two things must be equal. Solve for the terminal velocity. Now, it might not be clear to you, but this is what skydivers are manipulating when they're changing their cross-sectional area. They spread out, they make c a bigger number, that reduces the terminal velocity, so they slow down. Somebody's beneath them and they want to catch them, they make their cross-sectional area smaller, that makes c smaller, that increases their terminal velocity, they speed up. They see the ground coming, they deploy their parachute. Make the C incredibly big to to reduce their terminal velocity to as small a value as possible to make sure when they hit the ground they don't hurt themselves. Good so far? Pretty obvious? So the problem that we will have then is what begins now. Create, but do not solve, a differential equation that could be used to find a function for the velocity of the coffee filter. What does this velocity look like? Now, I know what the answer looks like, but you don't. Could be anything. We know the velocity is going to increase, but it's going to increase and then reach some terminal speed where it will stop increasing. That's what we know. You've probably seen functions that do this before. What your job is to find what that function is and what parameters control it. Now, making a differential equation is not anything complicated. We've already done it. But because it's been a long time and I didn't always use the terminology correctly, I want to refresh your memory. A differential equation is just an equation that has a differential in it. That's all a differential equation is. But to create the appropriate differential equation that could be used to solve for something requires a little bit of thought. So the first thing I want to remind you is that you know about a couple of differentials. These aren't part of our steps or anything, but you have two differentials at your disposal, things we learned back in August. We know that acceleration and velocity can both be written as a differential, as the rate of change of something. So we know that velocity is dx dt, and acceleration is dv dt. Creating a differential equation is going to require that we do substitution. We want to introduce a differential into our equation. So we need an equation that either has velocity in it or has an acceleration in it. Now, to know where to start is important. So whenever you are asked to create a differential equation, there are only a couple of starting points. Starting point number 1 is Newton's second law. Starting point number 2 is conservation of energy. There are potential other starting points. I've never seen them asked on the exam. In fact, I can't remember the last time that conservation of energy was a starting point. We will do an example of conservation of energy as a starting point, but I can't remember the last time it was on the exam. The number one way to do this is Newton's second law. For what I hope is obvious reasons. It has acceleration built in. And because it has acceleration built in, it's the right place to go. But you still have to use net force. You have to use Newton's second law. So before you can create a differential equation, you need to choose whether net force is the best way to go or conservation of energy is the best way to go. This one should be obvious. We know about the forces acting on the object, so we're going to choose the route where we use net force. So your first problem is to do the net force problem. This one's not a hard problem. mg minus cv equals ma. There. We've done the net force problem. Now, to create a differential equation, we need to substitute in for either the velocity or the acceleration with its differential alternative. Now, choosing which one to go there, I think is a no-brainer, but it might not be for you. If we put in dx dt, we introduce x, but we still have the acceleration there. If we substitute in dv dt, if we substitute in dv dt, then we introduce v, and there's already a v in the equation. This reduces the number of variables in our function. And that's what we want to do. We want to introduce a differential that is related to a variable in the function. We want to introduce a differential that is related to a variable in the function. Now, that's hard, I think, for young students to recognize. There's a lot of variables there. M is a variable, G is a variable, C is a variable, V is a variable, and M is a variable, and A is a variable. It's a lot of variables. I count 5 of them. Which ones are actually changing, and which ones are staying the same? once I drop the coffee filter, do you understand that M, G, and C are all staying the same the whole time? So although they are variables in an equation, they're not changing. They are going to stay constant while the coffee filter falls. The true variables are the things that are changing while the coffee filter is moving, which really means that A and V are the variables of this equation. Now look, I understand that it all looks like alphabet soup. That's the part that's hard of this class, is recognizing the situation, what things are staying the same and what things are changing. And I'm understanding that I need to be more careful about that. But now that I've identified it, I want to substitute in a differential that matches one of the other variables. V is a variable that will be there if I substitute in dv dt for A. So that is the right thing to do. I am going to substitute in dv dt for the acceleration. And that's it. We have created a differential equation that could be used to solve for v as a function of t. Now, by the way, the problem definition told you which differential to use. Just so you know, when I said in the problem, create a differential equation that could be used to solve for velocity as a function of time, I was telling you to use that. If I wanted something that would solve for the position as a function of time, then I would use that. So I was telling you which one to use. But I want to make sure you understand you could figure it out for yourself. Okay. That's probably worth 2 to 3 points. Doing the Newton's law stuff and doing the sub in for your differential. But now, if part B says now solve it, that's some work. It's going to be some work now. But be aware, the modern exam doesn't want this to be all math. They want there to be physics. This is more physics, what we're doing here. Solving this is less physics. So they give points for recognition of the parts of this that are physics, and they give fewer parts that are pure math. There's a lot of pure math to do in this problem, a lot. Almost an embarrassing amount. But pay attention, I will tell you where you're going to get points. First things first, I'm a realist. You need to be careful here. If you're being asked to solve for v as a function of t, and you're going to begin the process, modern exams will show you what the answer is. They'll say, show that the solution of this function is, and they'll give you the answer. So you're not getting points for getting the answer. You're getting points for demonstrating certain mileposts. I want to make sure I highlight what those mileposts are, and I will do my best. But you have to start with a correct differential equation. Now, the process we're going to use, we've used before. It's more complicated in this circumstance, but we've used it before. We're going to use the process of splitting the derivative. That's what we're going to do. It's kind of a form of separation of variables, but splitting a derivative. It's not particularly hard to do, and there's a number of ways to do it. I like to solve for my differential first and then begin the process, but you don't have to. So I'm going to do this the way that I just suggested, which is to solve for my differential first. It's uglier though. So if you don't like the way the ugliness looks, then maybe not do it this way. But what I mean is I'm going to get the differential to be all by itself, which means dividing by m, you're getting g minus c over m times v. I've written this in such a way that I've collected the constants and left the variables separate. So that's why I wanted to do that. That's a collection of constants. Now, so again, step 1 is to solve for your differential. Step 2 is to split the differential. So splitting a differential is easy. You just want to separate dv and dt. They're a fraction. So that just means multiplying both sides by dt. But that is the next step, is to split this differential after you've solved for it. So I will multiply both sides by dt. People who have had calculus or are in calculus should begin to see that we are building an integrand. That's what's happening here. For you guys who have never had calculus before, just so you know, we are building an integrand. That's what's happening here. We're building something that we can integrate. But to do so, we have to be aware that we have function variables that are changing. So we have another step to do before we can actually get to the calculus. And that step is we need to collect like terms. This is different than an algebra version of this. It's a little more complicated. dv refers to small changes in v. It will be our integrating variable on the left side. And dt refers to small changes in t. It will be our integrating variable on the right side. We need to get anything that has a t in it on the right side and anything that has a v in it on the left side. And you will only be able to do this by multiplying or dividing. There's no way to add this to both sides. So this entire function will have to be moved to the left side because that's where dv is. And there is no reference to t, so there's nothing to move to the right side. All right, now we have done everything we can to get this in form for us to be able to integrate. And that's the next step. When you verify that you have your function variable on the same side as your integrand variable, and that you have, no other variable on that side that is changing as time changes, then you're ready to take the integral of both sides. Now, just drawing the integral symbol isn't taking the integral. But, and this is important, in the AP Physics exam, drawing the integral symbol is good for a point. They want to know that you know you have to integrate both sides. So usually a point is given for splitting the derivative and isolating the variables correctly. So this portion is worth a point. And this part is usually worth a point if you do the following step. Now, this is where I need to clarify. You guys are in BC. You learn something different than what you have to do in this class. The AP graders want something done a special way here. They want you to do a definite integral and not an indefinite integral. You won't lose points if you do it as an indefinite integral, but they specifically look for the definite integral. So for those of you who have no idea what I just said, ignore it. Ignore all of it. So you guys who have never done this before, what you have to do is you have to tell the integral where the starting velocity and starting time is and where the final velocity and final time is. You see, on an integral, a number goes here to represent the starting point, and a number goes here to represent the ending point. Yeah, okay. So, the important thing, and what the graders are looking for, is for you to make sure you are matching what are called your boundary conditions. For example, our time very likely is starting at time 0. You released the coffee filter at time 0. They want to know that you recognize this represents something physical. And they want to know if you can synchronize it. At time 0, what was the velocity?
0.
So on the velocity side, we want to make sure that we start with the same velocity that the object had at time 0. We are applying a boundary condition, telling our system where to start. Now, this next part, bear with me. This is what you need to do, and it might be confusing. But we're trying to build a function. Our function is going to some unknown time in the future. So the top time is t. Sometime in the future. I get the fact that there's a t here as well. They're not the same t. If that bothers you, then use a different symbol. Use a capital T. Now you have to link these together. So on the left side, We are looking for a function. This is going to be v as a function of t. We're going to some function with respect to t that tells me the velocity for all times in the future. So we are setting the top boundary. There's almost always a point associated with setting the limits correctly on your integral. All right. Now that we've done all that, your next job is to integrate this and get a solution. Now, just point this out. We've not done very much math yet, but we're on minute number 25 from the point where we started. And we've got just a couple of lines here. It's going to take 3 times the amount to get to the end. It's not because what you have to do now is harder. It's because there's an incredible amount of algebra to do. An incredible amount. The calculus is going to be 1 line. But if you don't know how to do the calculus, you can't do any of the rest. And here's an important detail. Although there's a lot of algebra to do, almost all of what happens next is only worth 1 point. So if they've given you the answer and you make it to here, you may want to skip that point and finish the problem. There's probably something else they're going to have you do with that function. They gave you the function for a reason. But if you want to know how to go to the next route, we're going to go to the next route. Now, I want to teach you how to actually do the math, but that's not going to happen today. Well, not in 2 minutes. First, the right side you're supposed to already know how to do because we've done it before. Do you remember how to do the right side? If you don't, remember there's a t there, a hidden t. It is t to the 0 power because there's a 1 there, an implied 1. And because it's a polynomial, t to the 0 power, I know that the antiderivative requires that I take t, add 1 to the exponent, and divide by the new exponent. That's how I deal with polynomials. The only difference is that I have to still apply my limits. The right side is not a polynomial. The right side is more complicated than that. And knowing that I'm out of time, allow me just to tell you that doesn't quite look like
what you have to do next.
So let's maybe reorganize it a little bit. I bet we can reorganize it.
It's given to you.
For example, one of the things we could do
for this
is I could rewrite it
from here
as, let's see, dv over negative c over m v plus g. Now, if you don't know why I did that, then you know, let me call your attention to it. And this makes me feel a little bit like, I'm talking down to you, but that's not my intention. V is the important variable because I have dv on the top. So I'm placing the variable with v first, just like it showed me in the problem. Is that okay? No, it's not quite the same because I've got something out in front of v. And I had nothing out in front of x. Let's multiply the top and bottom of our fraction by negative m over c. So I'm going to get this out of my way a little bit, just so I have some place to work. And I'm going to multiply the top by negative m over c and the bottom by negative m over c. Right, this will free up v and make v all by itself. And it'll add the m over c to g. So let's just try it anyways. The right side is just t to the 1 power divided by 1. I'm just going to start writing t over there. That okay? All right, so another little trick, and you've been told this. I'm not sure you've been taught this, but some of these things are variables and some of these things are constant. I know they all look like variables, but they're not, right? We're dropping the coffee filter. That's what this was. Which of these things aren't changing as the coffee filter falls? Gravity is not changing as the coffee filter falls. Mass is not changing as the coffee filter falls. C is not changing as the coffee filter falls. Those are all constants. Right? That makes this basically A. It's just one number that is not changing. Now this sucker's in the top, and we had nothing in the top on the other one. But that's okay. It's a constant. Because it's a constant, I can take it and pull it outside of the integral completely. It's just multiplying everything by negative m over c. Fine. Not a problem. In fact, so not a problem, I'm just going to multiply both sides of my equation by negative c over m. Because if I do that, I get it out of the way completely. So I'll rewrite this as dv over v plus negative mg over c equals negative c over m times t, evaluated from 0 to t. Right? Just got rid of it completely by multiplying both sides of my equation by negative c over m. Good? Now, all I have to do is apply the... So I'm going to just go to the next line where I write in natural log, maybe. I guess I should not write in black. Natural log of v plus negative mg over c, evaluated from 0 to v. All right, so I have found the antiderivative of both sides. To complete doing the integral, I have to apply my limits. If you don't know how to apply limits, it's not rocket science, it is calculus. Applying your limits is straightforward. We have to tell our antiderivative where the function ends and where the function begins. That's all we're doing. So you start, and I'll do the easy one first. The one on the right is the easy one. We take our top limit and plug it in. So our top limit is t. We plug it in for the variable. The variable is t. So I know it seems a little redundant, but that's what we do. I plug in t for t. I then subtract and plug in my bottom limit, in this case 0. There, I have done it. I have completed the integral. Need to complete the integral on the other side, though. This one's got more stuff, right? So, natural log of, plug in v for my top limit, which is v. v plus negative mg over c. There, I plugged in my top limit. Subtract, and plug in my bottom limit. Natural log of 0 plus negative mg over c. I've done it. That's the answer. Kind of. We're done with all of the calculus and all of the differential equations and all of the physics, by the way. We've done all of it. Except this is not what they asked for. They asked for a function of v. They asked for v as a function of t. This is solved for t. So this is t as a function of v. So you need to solve this for v. I will remind you where v is right now. It's definitely hiding. Does not want to be found. Now I know all of you in BC, get going. You know how to do this. If you're waiting for me, stop waiting. You should know the algebra necessary to get here. You guys in AB should know the algebra necessary to get here, but I am familiar with Calc AB students, and I'm aware that some of them do not remember. Now, you guys who are in pre-calc, you've been taught all the things to get to V. Because the last thing you need is just a little bit of Algebra 2. But I am aware that your Algebra 2 teachers have probably not made logarithms a priority. So do me a favor, raise your hand if you remember your logarithm rules. I was afraid of that. Raise your hand if you remember the word logarithm. So the rules were taught, but it has been a while. So I'll say, and I am not a particularly good computer person. I just know a few things. All right, so that brings us here. We learned a lot. Now we can deal with this, right? Now, my belief is that I could just turn you loose and say, get it done. And all of you people who raised your hand and said, yes, I do know those things. You should be done with it by now. But I know better. I'm going to start by doing what the negative sign says to do, right? Combine those two things into a single. Now let me go back to using the easier to see. A single logarithm with V minus mg over c on top and minus mg over c on the bottom. There, we're good to go. And that has to equal negative c over m times t. You kind of see what's going to happen next, right? If I want to get v by itself, the next, are we good here? Everybody saw this all right? If I want to get v by itself, I need to get rid of that natural log. So I'm going to use that other rule and raise both sides to a base of e. I'm not going to write out the step where I raise them to the base of e. I'm just going to erase the logarithm and put the base e on the right. Is that okay with you guys? That's good. So I can get rid of the bars too now that I've done that. I want to get v by itself. I'm thinking multiply both sides by the denominator of that fraction. You guys good for that? Excellent. So v minus mg over c equals negative mg over c e to the minus c over m times t. Whew, boy, this has been a hard road, but there's only one thing left to do, and it's pure algebra. I'm thinking I don't even have to explain it to all of you. All you have to do is add something to both sides of an equation. Wow, that day one algebra 1. This is even back with like third grade, would it have like 3 plus box equals 5. You had to figure out what went in the box. The good old days. So v equals mg over c minus mg over c e to the minus, God, this thing is a mess. That's the answer. Kinda. This will not match the equation they showed you. So if you're wondering why the equation they showed you will look different than this, there's a purpose. There's one more thing they would like you to do. So you're done here. You will get 100% full credit if you end here, but there's a good reason to understand why this doesn't match what they will show you. They will do one more step, and you'll see why in a minute, but that step is to factor out the common value. That's what they will probably show you is the equation that you're supposed to show. It's not a big difference, I know, but there's a reason to do this. And I'll explain what that reason is right now. Everything inside the parenthesis is a unitless quantity. This is a very common exponential function. Very common. It shows up in nature everywhere. This function with different things and different parameters. It shows up in the charging function for a capacitor and an electronic circuit. It shows up in drag here. It shows up in music. It shows up in optics. It's everywhere. This is the reason E exists in nature and why it is here is everywhere in nature. It's not just in one place. It's awesome. Now, there's some points I want to bring up, but let's remind ourselves a little bit about what this took to get here, because I'm almost out of time. Oh, yeah. Oh, yeah. I leave that on the board, and people will never take this class, right? Oh, just a regular day in physics, no big deal. Yeah. Can I call your attention to this before the bell rings? How fast is it going at time equals 0? That's right, we just dropped it. Velocity is 0. And you remember that after a very long time, it reaches a constant velocity, right? Our expression should do that. T is here. Oops. T is right there. So, what is e to the 0 power? 1. So, v to the t equals 0 is going to be mg over c times 1 minus 1. Right? Isn't that 0? This one's going to be harder. What is e to negative infinity? In physics, we throw out infinity all the time. Infinity isn't as long as you might think or as big as you might think. Infinity can be just a couple of seconds. In the case of this, it's probably just milliseconds. Infinity isn't an infinitely long period of time. It's just long enough. So in the case of this, what is the limit of e as your exponent goes to a big negative number? 0. All right, so v of t going to infinity is going to be mg over c times 1 minus 0. That looks like a constant to me, doesn't it? The real question is, what does this look like? I would encourage you to take this function, put in placeholders for these numbers, and just throw it into your calculator and graph it. That is the very likely next thing that you would have to do on this problem, is to show what this would look like. Sketch a graph. We know that it has a starting point at 0 and an ending point that's at a constant of mg over c. What's the middle? You should prove it to yourself. There are 3 logarithm rules that you're supposed to know. And I don't know if you know them or not. I'm going to show you them. I'm not going to teach them. Because, again, a little salty. I've been told I don't do that. So I'm not going to do that. I will just show you. I need you to know a couple of logarithm rules. I need to know that you understand what you can do in situations where 2 logarithms are being added or subtracted. And I need you to be able to isolate a in the expression logarithm of a equals b, or the reverse. So, you remember that logarithms are exponents. So, you add exponents together when you multiply. So these logarithms can be combined because they're exponents. The addition of exponents comes from multiplication of numbers. On the other hand, a negative exponent goes in the denominator. So that suggests that if you're subtracting 2 exponents, you divide. I know you learned this. Well, maybe you didn't, but you were supposed to. It's in the curriculum. I checked this year just to make sure I wasn't wrong. I was not wrong. You also have to know how to get a by itself. And this one is probably the one you do remember, that I can raise both sides of an equation to the same base. This requires that you know that the base of a natural log is e. Now, I know you learned about other bases, like base 10 logs, base 7 log, base 4 log, whatever. But I don't know how much of that you remember, or what the purpose of learning about the different bases was. In the natural world, this logarithm shows up frequently. A more interesting question would be to figure out how they figured that out. That would be an interesting question. And if you pay attention in calc, they should explain it to you. It is a very interesting discussion where E comes from and how it was discovered. I will argue, though, that you should also know what this is. Do you know what it is? They cancel out, leaving you with A equals e to the b. I don't believe I have to show you that you can do the reverse of this, take the logarithm of both sides, but you should know that you could reciprocate this and go the other direction. I have shown you, not taught you, but I have shown you the three things I'm hoping you remember. We need two of these three things today because we subtract two logarithms. And then we have to get rid of the logarithm so we can get v by itself. We need those things. Are we good here? By the way, a set of these. Ignored every page but this one. Most of you have ignored. You shouldn't. There will be an integral table on your test. Let me start out by pointing out, this is what we just did for t, right? We added 1 to the exponent and divided by the new exponent. I know they're using x. X is a placeholder. If I replace this with t, I would have gotten t to the 0 plus 1, 0 plus 1 in the denominator. That is the polynomial rule. Do you see anything here that looks like our function? It's this one. Now, we're going to learn how to use the integral table tomorrow, and we'll finish this. In AB right now. If you're in AB, you're just beginning integration. Right? You're learning to make little rectangles or little trapezoids, and wow, we found the area under this thing. It's way neato. Yeah, you got a long way to go before you're taking this integral. I mean, you could, of course, plot this, but it has all variable names, and you have to try and somehow make a whole bunch of trapezoids, and that's just crazy what they make you go through to get to this point. But look, it's kind of like hazing to do this integral. You need to be able to do something called U substitution, and then from U substitution, you have to also know how to do the integration of 1 over the inverse. That's the process for getting this particular thing on the table. And so if you don't know how to do those integrations, you might as well just use the table to do it. But to use anything on the table, you have to make your integrand look like the integrand that is here. Now, if you don't know what that phrasing means, this part of an integral is called the integrand. It's the thing that you integrate. So not a particularly fancy word. In fact, they sound very similar, so I think we're pretty good to go. To use the table, you have to make yours look like this. And what that means is x has become the important variable. We are integrating with respect to x. And so the x variable should be here. And if there's anything constant, it should be here. Well, it's not exactly what we have, but that is what this is. That's what they've given us. Let's take a look at what's on ours in my sample. So to try and make this look as much like theirs, I want to try and, do what I can to get it to look the same. So I'm gonna try and be super clear, because I'm not teaching calculus now. I'm just teaching how to use a calculus table. This is kind of calculus, just so you know. So on the left side, our original integral is dv over v plus negative mg over c. That's what our integral looks like. And that suggests that the answer is going to be the natural log of v plus negative mg over c. Now, this isn't doing the integral. All it's giving me is the antiderivative. So it's saying if this is my integrand, this is my antiderivative. We still have to complete the process of doing an integral. And the process of doing an integral has more than one step, but one of the steps is finding the antiderivative. So for those of you who do know a little bit, who went through AB, you know that you could do this problem a little bit more, cumbersomely by replacing this with U, saying that U is going to be equal to V minus mg over C, finding out that du is equal to, dV? And then doing U sub. So you guys who have done U sub understand that. But if you haven't done U sub before, you got time. You got a whole semester after you're done finding all the trapezoids. You'll get to this stuff.